Okay, here I'm just going to do one more example of a thin film interference. This time we're going to put a thin film and we're going to add it to a glass mirror, and we're going to use that to increase its reflectivity. The coating on the mirror is going to be 1200 nanometers thick, and we're going to use this to determine any visible wavelengths that will experience constructive interference or will be reflected more by this mirror. So here's the film, which I said has a refractive index of 1.45. Here's the glass, which we will consider to be the glass of the mirror. And I said it was a 1.5. And here's air, which will be an n equals 1. And there's piece of light 1 and piece of light 2. Again, those lines should be directly over top of one another. I'm only drawing them side by side so we can see them. L2, in this case, will have twice the thickness of the film as that light penetrates and comes back out. And this time, for L2, if I look at N1 and N2 on the surface of reflection, I have 1.45 and 1.5. N2 is greater than N1, which means this is going to be fixed, which means I have an inverted reflected pulse. For L1, I'm looking at this surface here. I'm going from 1 to 1.45. So I don't have 2T, I never went into the film, but I do have an inverted pulse from my fixed end reflection. So now I can predict the path length difference that will be observed. 2T plus my inversion minus that inversion, and I'm just left with 2T. Now I want this to be constructive interference, so I'm going to make L2 minus L1 equal to n minus 1 lambda. And I get my little equation for relating the thickness to the wavelength. Now here, I need to be careful and remember that any wavelengths I get out of this equation are going to be in the film, so I'll be bringing them out of the film to figure out what they would be in the real world. So I have my thickness, I can find my wavelengths, and I want to try and find wavelengths in the visible spectrum. So this might be a little bit annoying, we might have to do a little bit of guess and check, but we'll get there pretty quickly. So in the visible spectrum, I'm going to have wavelengths from 300 nanometers to 700 nanometers or so. Okay? Now I'm going to solve this all for wavelength just to make my life a little easier. 2t, and I'm going to bring this n minus 1 down here. And then if I put my 2t in here, 2 times 1200 nanometers, I have to think, what values for n can I have that will result in this working out into this range? So probably the easiest way to do this is to take these two endpoints, put them in, and solve for n instead, and then look for integers that are in the range of those two endpoints. So let's put 300 in first. And so if I get 300, I'll bring my n minus 1 back up here. 2400 divided by 300. These are all in nanometers, so I don't need to change them all because they're all the same unit, so it's nice. Oh, hold on. I'm messing this up because these are the wavelengths in free space. And what I really want to do is I want to predict wavelengths in the film. So hold on a second. I'm going to take both of these guys and move them into the film. 300 divided by 1.45 and 700 divided by 1.45. And I get 300 divided by 1.45, so 207, and 700 divided by 1.45, 482. So that'll be the range of wavelengths that are visible based on the wavelengths in the film, not based on the wavelengths out. So let's just pop over here for a second, get our old eraser, get rid of you, and replace you with the minimum wavelength of visible light in the film. So 2400 divided by 207 is 11.6. So n minus 1. So n in this case would have been 12.6. So that'll set the low end of my range. And now I can do the high end of my range, 482 equals 2400 n minus 1, bringing the n minus 1 up, 2400 divided by that 482, oops, there we go, 2400 divided by 482, and I got 4.9, well, I'll just call it 5. So basically I need all the n values from 5 till 12. Oops, I made maybe a few too many options. I didn't mean to make that many, but that's okay. So I need to do 5, 6, 7, 8, 9, 10, 11, and 12. I'm not going to do all of those because they're going to be all the exact same, so I'm just going to pick 3. Why not? Okay? If I really needed this, like if it was important for something, not just some example on the internet, then I would have to go through all of those. It's not that big of a deal. Maybe I'd use an Excel file, but I don't have to go through all of those because I'm just doing this as an example. Anyway, here's the important equation that I'm going to use. Actually, I can even go down to, oh, that's fine. I'll start there. So lambda equals 2t on n minus 1. So 2 times 1200 nanometers on n minus 1. And so that'll be 2400 nanometers on n minus 1. Oops, sorry, this was 5. So when I bring that n minus 1, so n should have been 6. I made a mistake here. When I got this, this works out to be 5, and I forgot to bring the minus 1 over. So there you go. I shouldn't be using 5. I should only be using 6 to 12. Anyway, whatever. I'll do these 3. So 2400 nanometers on 7 minus 1 gets me 400 nanometers. Remember, this is the wavelength in the film, so I need the wavelength in free space. Wavelength in the film is equal to the wavelength in free space divided by the refractive index. So to get the wavelength in free space, I could go this 400 nanometers times 1.45. 580 nanometers. So this is the actual color that we would see reflect really well off of this mirror. Okay, that was for 7. Let's do 9. Lambda equals 2400 nanometers divided by 9 minus 1. So 2400 divided by 8, it's 300 nanometers. And again, I gotta take that out of the film. So my lambda in the film is 300 nanometers. My lambda out is what I'm interested in. My refractive index is 1.45. So if I go 300 times my 1.45, I'm going to get a lambda original of 435 nanometers. So, I don't know. I said I'd do 3. 2 is enough. You get the idea. I would have to go do that for that, and I would get all of the wavelengths in my visible spectrum that would reflect strongly from this mirror. So this would make an excellent mirror for light at 580 nanometers or green, or a really, really good mirror at 435 nanometers or something that's sort of purple. And so that's how this reflection coating would work. So that's thin films. I'm going to stop doing examples now.